So from time to time, I gave you a thinking exercise about dice, and I claimed that this will be related to differential cryptanalysis. So let's look at it for the last time and see why this is important to understand how differential cryptanalysis, or actually how any statistical attack works actually. So the thinking exercise was as follows. You are given a dice and you are allowed to roll it to see the result as many times as you want. You are asked to determine if the dice you have is a fair dice or it is a biased dice which rolls 6 with probability 1/3. What would you do? So the thing is that for the fair dice, you roll 6 with probability 1/6, but for the biased dice, you only have the information that you can roll 6 with a better probability, which is 1/3. So if you already think about the question, or if you, after seeing what we have talked about differential cryptanalysis, maybe you can see how you would approach this problem. For instance, assume that you have the dice, and let's say that you rolled it 60 times. So what is the expected value of seeing the rolling 6? How many times you would expect to see the 6 on the dice? So if it is a fair dice, since it has probability 1/6 for rolling 6, and if you roll it 60 times, you expect to see 60 divided by 6, which is 10 times. So your expected value is a 10 for the fair dice. But for the biased dice, if you roll it 60 times, 60 times 1/3 is 20, so your expected value becomes 20. So when I give you a dice and you roll it 60 times, and if you observe, for instance, 25 many sixes, you will say that, okay, this dice is biased. Or if you see like 12 times, you will see that it is a fair dice because it is closer to 10 than 20. But question is, what would you say if you rolled, if you observe 6 15 times, because 15 is equidistant to 10 and 12. So you cannot now you cannot distinguish which one it is. So you might say that, okay, I will roll it more times so that the expected values become distant to each other. So if you perform this experiment for instance, 600 times, expected values becomes 100 and 200. So the distance between them is now increased. So if you, for instance, do this experiment for 6 million times, then the expected value becomes 1 million and 2 million. So now they are really distant to each other. So your experiment would succeed almost definitely. But the problem is that you cannot roll a dice 6 million times. You wouldn't have the energy or the time. But also, if you think about this in an attack, in a distinguishing attack, rolling the dice 6 million times means actually you're performing an encryption operation or checking some property for 6 million times, which requires computational power. So as you can see, increasing the number of experiments actually means that increasing number of data, and since you perform operations on the data, it also increases your time complexity. So in this case, this question is actually how we try to solve the distinguishing problem. In order to distinguish two things, they should be observed with two different probabilities. So probability should be different for a random permutation and for the cipher that you are attacking. And but when we turn it to a key recovery attack, now there is only a single correct key and a lot of wrong keys. So the exercise actually turns into a problem where you have many dices, but only one of them is biased. So you are trying to find that biased one. So this is the idea behind it. Actually, this is a comparison of binomial distributions, their expected values, and see how successful we are. So if you go back to our example, I said that we can maybe roll the dice 60 times or 600 times, but now question is, what would be our success probability? So because, for instance, assume that we roll the dice 60 times and we observed 16 times 6. So we claim that this is a biased dice, but maybe it was a fair dice and you were very lucky and you rolled a lot of sixes. So this would be a false alarm for you. But similarly, it could be a biased dice. You roll it 60 times, but observe 6 only 14 times, and you say that it is a fair dice. Then this means that you don't detect it, so we call it a non-detection. So what will be the probabilities of non-detection or success probability, or another way of looking at the problem? In order to be successful for 99.9% of the time, how many times should I roll the dice? So these questions actually arises when you are performing a statistical attack, because you need to know how many data you need and what will be your success probability. So let's give a few notations, actually variables, and then look at how it is done in the literature. So let's assume that P is the probability of the distinguisher for the wrong key, and P0 is the probability of the distinguisher for the correct key. PFA is the false alarm probability. PND is the non-detection probability. N is the number of plaintext ciphertext pairs you need to use to perform the attack. So N will be your data complexity at the end. T is the threshold used to decide whether the key counter is a candidate. So if you go back to our dice example, you consider the example where we roll it 60 times. I said that the expected values become 10 and 20. So 15 is the middle of these expected values. So my approach could be, let's say that if it is higher than 15, I will say it a biased dice. If it is less than 15, I will call it a fair dice. So at this example, 15 is our threshold. So actually we need an algorithm where we can put the threshold and say that with this threshold, with this N, our success and non-detection probability, our non-detection and false alarm probability is this, and so on. So we need such a calculation, but we cannot perform all the time these calculations by ourselves, because the numbers are most of the time really huge, and we cannot perform binomial distribution operations with huge numbers. So what should be our perception? We can look at the problem in two different ways. Assume that we are given n, so this is the number of data, so you captured n many plaintext and ciphertext pairs. You find a distinguisher, so you know the probabilities of it for a wrong key and the correct key. Then what is the success probability of the attack for this n? This is one way of looking at the question. Another way of looking at it is that you find a distinguisher, so you again know P and P0, so probability for a random permutation or a wrong key, and P0 is the probability for the correct key. But you also choose probability of non-detection and false alarm probabilities by yourself. So with these choices and with this distinguisher, how many pairs we need to perform the attack? So what would be the n in this case? So you can look at the problem with these two ways. And actually, now we will talk about Ali Aydin Selçuk's solution, which actually answers the question in this respect. Then we will look at Blonde et al.'s algorithm, and which answers the question from this perspective. So, but first recall what a binomial distribution is, and let's see why this we cannot compute these values by using a computer. So we have n pairs, and the distinguisher is observed with probabilities P and P0 for two different cases. One is now for the distinguishing attack. P is the probability for the permutation, random permutation, and P0 is the probability for the cipher, which you find the distinguisher for, which has a weakness. But if it is a key recovery attack, P becomes the probability of observing the distinguisher for a wrong key, and P0 is the probability of observing the distinguisher for the correct key. So we are trying to distinguish two binomial distributions with parameters MP and MP0. However, it is computationally infeasible to calculate the non-detection or false alarm probabilities. For example, when you put the threshold T, non-detection or the false alarm probability depends on which side of the T you are looking, would be something like this. Summation of I from 0 to T, And if you are looking on the other direction, it will be summation from t to the n, the big N. But this calculation, this small n is also should be capital N. So it will be a combination of n with I times p0 to the power I times 1 minus p0 to the power n minus I. This is for the probability of the correct key. But the problem is that we cannot perform such a huge summation because n is most of the time is something close to 2 to the b. And p0 is sometimes has probability very close to 2 to the minus b. So regardless of where you put the threshold, this summation would be very hard to compute. And t is most of the time something like n over 2. So it is a very summation of huge number of numbers, which are powers of huge powers of very small numbers. So it is not easy to calculate. So instead, in literature, Alayda Selçuklu does the normal distribution approximation of the binomial distribution. So there's again a typo here. Selçuklu uses the fact that binomial distribution can be approximated by normal distribution when n is large enough, and in our examples, n is really large. These formulas provide good success probability approximations for differential and linear cryptanalysis when the inputs n, p, p0 are provided. So just using his approximations, you can get the success probability by using these values. Blonde et al. Also more recently, let's say, because this work is later than Selçuklu's work, they use approximations for binomial distribution, so they don't do a normal distribution approximation, but they perform an approximation directly for the binomial distribution operation, namely actually to this part. This combination is actually permutation, so combination is performed with an approximation. So their algorithm takes input as p, p0, false alarm probability and non-detection probability as input, and as an output, it provides n, which is the number of plaintext cipher text pairs you need, and t is the threshold where you should decide if a key is a correct or a wrong one. So in literature, there are these two approaches. Actually, you don't have to use them. For your attack, you can also approximate the success probability by yourself, but most of the time, this is a tedious approach, and people prefer to use non-approximation. Selçuklu's formulas is very simple and works for differential and linear cryptanalysis, but this work is kind of more general. You can even use it for, I think, impossible differential attacks and so on. And actually, it looks to the problem from a different perception. So you don't need to decide n yourself, but you decide the false alarm and non-detection probabilities, which will actually eventually will give you the success probability.